Shown in figure is a three-phase star-connected induction motor equivalent circuit. Okay, the motor has stator impedance of 0.06 plus J times of 0.2 ohms and an equivalent rotor impedance of 0.06 plus J times of 0.22 ohms. Okay, neglecting the current, what is the slip at which maximum gross power can be delivered? Okay, he has given the stator impedance means what is the stator impedance 0.06 plus J times of 0.2. So what is the total resistance we have? Stator plus rotor is 0.06 plus 0.06 in stator and rotor winding. So this is 0.12 ohms. Similarly, what is the total reactance present in stator and rotor? Xt is equal to x1 plus x2 dash, which is equal to 0.2 plus 0.22 0.42 ohms. So what is the total impedance, that is rotor is referred to stator plus stator winding as 0.12 square plus 0.42 square, which is equal to 0.44 ohms. Now what is the slip present at which maximum gross power which can be delivered? So this is given as R2 by R2 plus Z0 1. What is the value of R2? 0.06 plus 0.06 plus 0.44. This is equal to 0.12, which is equal to 12%. So option C is the correct answer. Transformer is connected to a 1000 volts 50 Hz supply. The total core loss is 1000 watt, of which 700 are hysteresis and 300 watts is eddy current loss. If the applied voltage is raised to 2000 volts and frequency is equal to 100 Hz, what is the new core loss? Okay, earlier he has applied voltage of 1000 volts, okay, with frequency of 50 Hz. So V by F is equal to 2. Similarly, after that, voltage is raised to 2000 volts, whereas frequency is raised to 100 Hz. So V by F ratio is equal to 2. So that means the V by F ratio is constant. Okay, if V by F ratio is constant, a core loss is given as hysteresis plus eddy current loss. Okay, when V by F ratio is constant, hysteresis loss is directly proportional to frequency F, whereas eddy current loss is proportional to F square. Okay, if V by F ratio, which is nothing but an B max. Okay, generally hysteresis loss is directly proportional to B max power 1.6 into F. If V by F ratio is not constant, then what this one? It is directly proportional to V power 1.6 F power minus 0.6. Similarly, hysteresis loss is directly proportional to Bm square into F square. When V by F ratio is not constant, this is directly proportional to V square. So we should not use this formula since this is valid for V by F is not equal to constant. So we have to use only these where V by F is equal to constant. So I can write this one as WH2 by WH1 is equal to F2 by F1. So what is hysteresis losses 2? Hysteresis losses 2 is equal to hysteresis losses 1, okay, which is of 700 watts. So this is 700 into 100 by 50, which is equal to 1400 watt. Similarly, WE2 by WE1 is equal to F2 by F1 whole square. So I can write hysteresis losses 2, that is at 2000 volts, is equal to hysteresis losses 1 is 300 into 100 by 50 whole square, which is equal to 1200 watt. Now what is the new core loss? WC2 WH2 plus WE2, which is equal to 1400 plus 1200, which is equal to 2600 watt. So option D is the correct answer. I-bus matrix of a 100 bus interconnected system has 90% sparse. Hence, the number of transmission lines in the system must be, okay, suppose if you have a Y-bus matrix, generally this matrix is rated for n by n. Okay, here number of buses is equal to 100, so this matrix is of order 100 by 100. Okay, so total number of elements is, total elements in this matrix is 100 into 100, which is equal to 10,000 elements are present. Okay, all these elements, let us take, see here, this is transmission line 1 2 3 4 so on to 100. Similarly, number of rows are 1 2 3 4 so on to 100. Okay, suppose if you have a 3 bus system, let us take this as 1 2 and 3. Okay, the interconnection of the buses, let us take it as like this. Now transmission line means it is connected between two buses. Okay, let us take this transmission line, it is connected between 1 and 2. Similarly, this is a transmission line connected between 1 and 3. Similarly, this is a transmission line connected between 2 and 3 as well. Okay, see here, transmission line means it is an interconnection between two nodes. We can treat each bus as a node, so it is interconnection between two nodes. Okay, out of these 10,000 elements, 90% is sparse. That means only remaining 10% has non-zero elements. What do you mean by sparse? The entry is 0. Okay, most number of elements in this 100 by 100 matrix is zeros. Okay, only 10% is having non-zero elements. So 10,000 into 10 by 100 is equal to 1000. Out of these elements, 10,000 elements, these are non-sparse elements. That means non-zero entry elements we are having. Okay, now how many number of self-admittance elements are there? All diagonal elements are called it as self-admittance. Remaining are called as lower and upper triangle are called as mutual admittance values. So how many are there? These non-diagonal elements are exactly 100. So number of self-admittance elements for 100 bus system is equal to 100. Okay, so number of transmission lines, so non-zero elements are nothing but transmission lines. Okay, 1000 minus 100, which is equal to 900, because these are non-sparse elements. Okay, self-admittance means, what is self-admittance? Suppose this is having transmission line of admittance y1, y2 and y3. Self-admittance at bus 1 is y1 plus y2. Similarly, self-admittance at bus 3 is y2 plus y3. Similarly, self-admittance at bus 2 is y1 plus y3. So we have to subtract non-zero elements, non-zero entry elements from these self-admittance matrix elements. Okay, so it is equal to 1000 minus 100 as 900. So number of transmission lines in the system must be 900, which is option C. Y bus matrix of a 100 bus interconnected system is 90% sparse, then the number of transmission lines in the system must be. Okay, now Y bus matrix is of order n by n, where n is equal to number of buses. Okay, in question he has given as it is a 100 bus system, so total number of elements in n by n matrix is, total number of elements is n square. So this is 100 square, which is 10000. So there are 10,000 elements in this Y bus matrix. Now this Y bus matrix is 90% sparse. Now what is sparse? If element entry is equal to 0, okay, then it is called as, if more number of elements are 0 in the matrix, then it is called as sparse matrix. So out of this 90% are sparse, so number of non-zero elements, okay, that means only 10% of the Y bus matrix is non-zero. So this is 100 into 100, that is 10,000 into 10%, so this is 10 by 100. So number of non-zero elements is 1000. Okay, now what we have to find here? Number of transmission lines. Now transmission line is connected between two buses. Okay, like this. Between any two buses, transmission lines will be there. Okay, so what is out of these 1000 entries? Okay, how many self-diagonal elements are there here? Self-diagonal elements are, since it is n bus systems, n by n matrix system, okay, total number of self-diagonals is equal to n. So n is 100. So number of transmission lines in the system is 900, which is option C. A 800 kilovolts transmission line has per phase line inductance as 1.1 millihenry per kilometer, whereas per phase capacitance is 11.68 nanofarad per kilometer. Ignoring the length of the line, its steady state power transfer capability in megawatt is. Now, what is steady state power transfer capability? Which is equal to V square by ZC. Now, what is ZC here? ZC is square root of L by C. So, this is square root of L is 1.1 into 10 power minus 3 divided by 11.68 into 10 power minus 12. Okay, so power is equal to V square is given as 800 kilovolts. Since we have to find in megawatt, unit will be 800 into 10 power 3 whole square, which is 800 square into megawatt divided by ZC. Okay, you will get the answer as 2085 megawatt, which is option C.
RLC circuit, Vs is 400 volts, which is RMS value, and R equals to 20 ohms, and inductive reactance is 40 ohms, and capacitive reactance is 40 ohms. We have to calculate the Q factor of the series RLC circuit. Here, in the data itself they have given as XL equals to XC. That means the circuit is at resonance. In that case, the Q factor is omega naught L by R. Omega naught L is nothing but XL by R. XL is 40 divided by 20, which is equals to 2. That is, option A is correct. Comes to the second part B, the voltage across the inductor. VL is nothing but IXL into 90 degrees. Here XL is 40. I is nothing but 400 volts VRMS divided by 20, that is 20, which is nothing but 20 into 40 at 90 degrees, which is 800 at 90 degrees. That is, option A is correct.
Series motor is supplied from single phase half control rectifier. Single phase half control rectifier is nothing but single phase semi converter. Okay, so we have a semi converter which is of single phase. Okay, converter means it is converting AC to DC. At the output side we have a DC series motor. Okay, this is DC series motor. Here we have a field winding in series to the DC motor. Now let us take, this is the output voltage to the motor, to the converter, and this is the input voltage, terminal voltage to the motor. Okay, now he has supplied 230 volts 50 Hz from the input side of the single phase half control rectifier. The armature and field resistance together is, he has given it as 0.25 ohm, and load torque T is equal to 25 Newton meter. Neglect damping and motor constant at rated conditions is, okay, he has given some constant K is equal to 0.25. This is volt per ampere per radians per second. Okay, this is the data given by him. What we have to find? We have to find average armature current, okay, for a terminal voltage of 210 volts. At the same applied voltage, what is the speed of the motor? Okay, now let us see the first question here. Now, output voltage of the converter is equal to terminal voltage, that is input voltage to the motor, DC series motor. Output voltage of single phase half control semi converter is given as Vm by pi into 1 plus cos alpha. Okay, now what is the terminal voltage of the motor? Terminal voltage of a DC series motor is given as EB plus IA into RA plus RSC, since it is of series motor. Now what is EB here? EB is equal to back EMF. In series motor we can write with some constant K into, okay, IA into omega m plus IA times of RA plus RSC. Okay, now what is the terminal voltage applied to the in motor? It is given as 210 volts. So this is 210 is equal to, okay, IA times of I can write K into omega m plus RA plus RSC. Okay, now what we have to find? We have to find average armature current. Okay, we know that torque is equal to some constant K into Ia square for DC series motor. Okay, this is up to saturation. After saturation, Ia remains constant, torque is directly proportional to only armature current. Generally in DC motor it is directly proportional to square of armature current. Okay, now what is the constant value he has given? Constant value is given as 0.25. Okay, rated torque is 25 Newton meter into Ia square. From this I can find average armature current as square root of 100, which is equal to 10 amperes, which is option A. Okay, now next question, at the same applied voltage what is the speed of the motor? At the same applied voltage 210 volts, now what is the speed of the motor? So 210 is equal to this equation. Okay, Ia value got it as 10 amperes, constant K is 0.25. Okay, omega m is 2 pi into n by 60 plus Ra plus Rsc is equal to 0.25. From this we can find n value as 793 rpm, which is option B.
The initial contents of DE and HL page are given as 5472H and 4528H respectively, and all the flags are set initially. So for the following program we have to find out the following, we have to answer the following questions. The value of the accumulator after the execution of the program RET. So we have to find out the accumulator content after the execution of the program. Here in the first case, what we are trying to do is we are performing EL addition, and then after we performing DH addition. So after complete addition we are keeping MVI. Before executing a written instruction we are loading A with 00. So the accumulator must contain the 00 before means after execution of written instruction. So the data is not going to be affected after written instruction. So option A is correct. Comes to the carry flag is set to. See, after the written instruction, the carry flag is depends upon the last arithmetic instruction before execution of RET. The rotate left carry, rotate accumulator left. That is, here this is the accumulator content. Here 1 to 8, because accumulator is an 8-bit resistor. This is a carry flag. This is D7th bit, D0 bit. RLC instruction keeps the D7 in carry as well as here. So D7 bit before performing RLC, accumulator contains 00H. So 0 is going to be pushed into the carry before written instruction. So after execution also carry flags are not going to be affected because of written instruction. So option A is correct.
Kilovolt 50 Hz single phase cable has a diameter of 20 mm. That means, let us take, we have a single phase single core cable. Okay, diameter is 20 mm, so radius is 10 mm, and an internal sheath radius of 15 mm. Okay, the sheath radius is given from center of the core to the sheath as 15 mm. Okay, radius is 15 mm. If the dielectric has relative permittivity of 2.4, okay, this is, he has given it as 2.4, so epsilon r is equal to 2.4. Okay, now, and a loss angle of 0.031 radians. So delta is loss angle, that is 0.031 radians. If the length of the cable is 2.5 kilometers, okay, length he has given as 2.5 kilometers, then the capacitance of the cable is, we have to find the capacitance of the cable. Now what is the capacitance of the cable? Capacitance of a cable is given as 2 pi epsilon naught epsilon r by ln capital R by small r. Capital R is radius from center of the core to the sheath, small r is radius of the core. Okay, this one is core, whereas this is sheath in the cable. Okay, this is farad per meters. Now this 2 pi into epsilon naught is 8.854. I can write this one as into 10 power minus 12 into 2.4 divided by ln capital R by small r. Capital R value is 15 mm divided by small r radius is 10 mm. Okay, this is farad per meter. Now you can find it this one as 0.329 microfarad per kilometer. Okay, now he asked capacitance of a cable for 2.5 kilometers, so this is 0.329 into 2.5, which is equal to 0.823 microfarad is the answer. Okay, option B. Now what is the second question? If the no load current is approximately taken as charging current, then the value of charging current is, okay, charging current is given as IC is equal to V into omega C, or you can write this one as V by XC. Okay, now what is the value of V there? V is equal to 11 kilovolts. Okay, omega is 2 pi into F. F is 50 hertz into capacitance value is 0.823, 0.823 into 10 power minus 6 farad into single phase line, so we should not divide by root 3. Okay, directly this is single phase line, RMS value is 11 kilovolts. Okay, you can find it this one as 2.84 amperes, which is option A.